Okay, welcome everyone. I hope you can hear me okay. Um, Welcome to our um, tutorial for linear regression lab number 2. We'll take you through some basic ideas first and then we'll get cracking on some other things as well. Alright, so lecture 2 was fairly comprehensive and I'm just wondering, hello to everyone. Hi James and Matt, can you hear me? Can you guys hear can you just tell me if you can hear me? Albert, Luke, you can hear me okay? Very good. Alright, thanks very much. We'll get on. I'm recording this one today. I'll talk to Joanna about posting it, but it'll be a YouTube video that I'll put up. So that'll be something that we can look at. Now, an interesting feature of the Zoom chat is that it likes to sit on top. So you'll forgive me if I'm looking over that way, checking things out. It'll be that way, checking things out because I have to do that. Alright, so with your lab for today, we'll walk through that. I've got everything pretty much set up. And just thinking about the main aspects of this this guy here, and basic ideas don't change when you move into these are our estimations. So this is for a population. It's got the error in it, and then we've got the model, and you'll notice that the error is missing. So that's the first couple of things. I'm just going to run through a couple of ideas first before I come back to the lecture and before I come back to the actual lab, and we'll start going through the lab. Okay. Alright, so we've got our beta column here, beta 0. So there's some ideas there. Now, one of the things that we looked at in your lecture where you were looking at the usual ideas of hypothesis, and I'll go through that again. Also, we were looking at sorry, I'm just making a couple of adjustments here as we go along. Thank you. So we were looking at the testing and the hypothesis testing. That won't change. We still do that. And then we're looking at t-tests and looking at the computations for t-tests, hypothesis testing. I'll walk through that again because that's an area that people like to look at. But then what we started to do was the models, and we introduced this concept of the f-test. Now, what's the f-test all about? Okay, when we looked at the f-test and basically keep going down, what was that about? So we're going to have a little look at that. And leverage and influence. What was leverage and influence all about? Okay, so the lab today draws out a couple of ideas related to f-test, and it relates to r squared. So we'll be having a look at r squared again, and that's all in the lab. Okay, so leverage and influence, there's a little bit of a discussion there about leverage and influence, and also we'll be looking at the implications for that. Now that's an Anscombe's data set. Now this is the big thing for today, okay? The big thing for today is your assumptions. You need to be assured that in any examinations that you do in your regression assumptions, you'll need to be aware of what those regression assumptions are, and so we need to cover that today as we go through our lab. Okay, so a couple of summary type points for assumptions. There's a lot done in terms of there's our model equation for the population, and that's our hat. Now our hat is our estimator. Whenever you see a hat, you use the word estimator. You might want to write that down. Hat means estimator. So the estimator gives us an idea of what the model is. Okay, now I want you to write this down. Okay, this is very important because this is something that we need to come to terms with in terms of our modelling. Okay, so we want this to be very clear in your thinking what does this error, a random variable with a constant variance, what's that all about? Okay, so we needed a concept to get that nailed down today. All right, checking your model assumptions. So there's a couple of things that we'll talk about in terms of assumptions, and we'll be looking at those. Okay. Residual analysis is based on these assumptions around error. So errors and residuals. So we're going to link all that together, and hopefully be able to pull that together with your lab. Okay. We'll give some explanation again about this. I've got some simpler things that I want you to have a look at. Okay, and then we get to R squared and analysis of variance. So Cook's distance comes up today as well, so that's in the lab. So we'll be going through all of those things that link in with our lab today. Okay, so please don't be alarmed or concerned by my rushing through that part there. Okay, so the next thing we want to have a look at is our Word document. Okay, so that's our regression analysis. So let's have a look a little bit at what we can do for regression analysis assumptions. So these are Jason's version. I mean, I wouldn't be too hung up on, the sources and things, but basically, is the underlying relationship or the nature so these are the things you'll need to be able to nail down for any kind of assessment or exams that come up. What are your assumptions? Okay, what are your assumptions? So is the underlying relationship actually linear? So we can't use linear regression if it's not linear. So we can use other forms of modelling, but for our purposes. Okay. The next thing is we want to think about the independence of errors. Is there some mechanism honing itself into our data set, the independence of errors? And I'll use that because this is where our errors come in. Okay, so I've got a little bit of fun for you, and so I'm going to just grab that little bit of fun for you. I'm just going to go away for a second from my mail. That's not it. Sorry, I'm still looking. That's that one. Okay, so let's try this. Oh, we'll get there. That's the one I want. Okay, very good. So I'll leave you guys to look that up yourself. I don't think the word's been used in the notes, but the interesting part for me is pronunciation. Emma's saying. So a bit loud. Let's let that skip ahead. Okay. That's a complicated word. Can you guys hear that? Homoscedasticity. Homo. Okay, so it's not playing because I am using my earphone and microphone together.
City.
Okay. All right. So enough fun. Enough of that. Okay. So homoscedasticity. That's the bit I want to write down here. Homoscedasticity. it's not important on one level. Sedasticity. But what does it mean? Homosedasticity. Sedasticity. If you want to break it up, homosedasticity, it talks about constant variance. So for constant variance, it's important. Okay, homosedasticity. Can you guys still hear me okay? I haven't mucked that in any way. Are you guys still hearing me okay? Still loud and clear? Thanks, Luke. Yeah. Okay, so homosedasticity is about constant variance, and all of these regression assumptions relate to our analysis of errors. So the next thing, of course, is normality. So in summary, I think this is what came out of your lecture. So Y values are normally distributed for each x. I'll come to another explanation of what that is. And the probability distribution Okay, so that page there, I think at some point all of the labs and all of the things that you're engaging with are designed to help you get to the reality of what that is. Okay, so all of those things there. So either take a screenshot. I hope you've got a screenshot. You can look at the video later if I post it. And basically we need to see that they're linear. We need to see there's an independence of errors. We need to see that homosedasticity is there, that is constant variance of our error terms, and normality, Y value is normally distributed, and probability distribution is normal. So from today, in going through the lab, hopefully we'll hone in on all of those guys for you. Okay, so that'll be something that we'll be looking at. All right, so in terms of that, I just want to do this one. Okay, so what does it mean for some of those terms? Well, we'll work through the lab, and we'll bring those up as they go, as I want to do. All right, so the first thing is for the lab, we get the data and we bring it in, and I've already got the thing open. So we've got our data open, and if we can just keep the comments focused to what we're doing here. You guys are very good anyway, but the university's hypersensitive at the moment about what's happening on Zoom, so I just encourage you to hop off and send each other emails or do something external. I know I'm a boring dude, and I know it's a long time, but hey, there you go. Alright, so we've got our model. Some of you may have already done all of this. So in terms of our procedure, regression, linear, it brings up the box. We'll use the box the way it's represented here. Click on statistics. We're going to, under regression coefficients, check confidence intervals. 95 is already there. Okay, and under residuals we're going to use the DW checkbox. So this one here is something that you'll be using. Alright, if you're asked questions about residuals, I don't know that I put that on as a reference to residual analysis, but I'll just continue that. Okay, now we've got to put in our dependent and independent variables, so scores our dependent and ours are our independent. Okay, and then we can press OK. Alright, very good. So we've got our initial data set, and we've got our summary, we've got our coefficients. This is the one that you're interested in, particularly around exams, in terms of analysing your exams, getting prepared for your exams. this is the coefficients table that you're interested in. Understanding the significance, which is basically your p-values. So if you're not writing this stuff down, you should be writing this down. P-values, and talking about your B. So here's your BO and your B1. Okay, your BO and your B1 and your standard error. So we're going to refer to these, and your T statistics. So we're going to refer to these through. Okay, all the way through this part. Okay, so I dumped out of that a little bit early, but that's fine. You may do the same thing, so that's alright. It's okay if I do that. And if we go to linear again, we're just back here. This time we'll do the plots, which is part of what we're doing here. And the standardized residual plots. Check histogram and normal probability plot. Okay, so once we've got that, and we can press continue. Very good. Alright, after that, we're going to go to save and predicted values. We want the unstandardized version. Residuals, we're going to have a look at residuals. Distances, and continue. Okay. Okay, so this is the part of the an interesting idea here. We begin by checking the residuals as a proxy for checking the errors for compliance with the modelling assumptions. Okay. The assumption of normality, it's a histogram and a PP per plot, and it's given here. Okay. So in that regard, I'll just get out a plot, and sorry, I've got a million things open, and here's our plot. Now I want to compare that with something else, and I've got a little version of a picture here that talks about residual plots. So I'm just going to bring that over for you to have a look at. Okay, so basically what's this talking about? This is kind of everything you've been doing in a nutshell, I guess. This is an example of a residual versus fits plot for shows constant variance and no obvious pattern. So this is a simplified version of what's coming up in your work thus far. Okay, so in here, you may have seen this before when you did your intro to stats type arrangement, but I'm just bringing it back for you to have another look at. So we've got our fits, and what we're looking for our residual analysis whenever we do this are these two diagrams at the top. These are the things that we're interested in. For a normal probability plot, we'll get our residuals. You'll notice this is the residuals on the bottom here. Your residual plot will show that the residuals are hugging a linear model very carefully. So we're talking about the residuals or the errors related to our data. Okay, not our data itself. This is not plots of the data itself. It's a plot of residuals. For the fits, the residuals versus fits, what this guy's doing here is telling us about variance. Okay, this is telling us about variance. And so if it's random in nature and the variance is the same for our fits, then what we're able to say is that our assumptions, our underlying assumptions about what's happening with our regression model is in a good place. Okay, so we need to be able to just cogitate for a little bit on understanding the nature of residuals and how they work to inform us about the quality of our regression model. Okay, so putting it in terms that's a bit simpler so that we can follow that. Alright, so let's just go back to our fits here. Okay. Alright, so And that looks not unlike what we just had a look at. Okay, so we've got a histogram for our standardized residuals, and we've got our dependent variables and our residuals, standardized residuals. Okay, so to check the normality plot assumption, we visually check the blue on histogram against the theoretical plot, solid on both plots. Okay, if they match approximately, we assume that the conclusion is met. So this assumption, these assumptions are a big part of what you're doing in this part of the course. Okay, any kind of examination that you get will be zeroing in on this idea of assumption. Okay. All right. So in your, sorry, I get things clicking around. It drives me off the wall, but that's not yours. That's mine. Okay. So when we're dealing with now your standardized residuals are the observations minus the predictions. Okay, standardized just means standardized residuals just means your observations from your predictions. Okay, so E, it's got an index I, so it's about the data components itself. So a sub I, and so we've got E is observations minus predicted. So there was a comment there about what are standardized. So that's our standardized. Yes, the variance of residuals. Good, good. So what's the variance of residuals? Okay, so yes, that's what we're looking for. So the normality assumption is about the residuals, and also this close fit is also about whether or not we've got normality. So if we've got a normal distribution and we've got similar variances, and I'll explain some more of that as we go on, then we've got a very good starting place. Okay. All right, so what's the comment? Use the histogram and the PP plot of the standardized residuals. Comment on the assumption of normality. So what would your assumption of normality be? We've got a close empirical plot, okay, and with assumption is visually checked, and a theoretical plot, and we say that it's a good, using the histogram, we can say that our assumption of normality is good. Using the residuals for the close fit, we don't see that it's wildly different from the model, and so we can say that both of those are a good fit. Okay. All right. So in that sense, we've got a fairly good idea of that part. Okay. So I'm just checking a couple of facts. Very good. Okay. Okay, very good. All right, so at this point, we're looking for, so that's your part A. All right, based on what I've shown you previously, if we've got a cluster that looks like it's fitting normally, it's a little bit clunky, but it's not too bad. It'll be blatantly obvious if it's not. This one here, the fits, is very important. Okay, so the cumulative probability for fits is very important, and so we need to be able to see the linear nature of that. Alright, so we can also check normality statistically via hypothesis tests. So let's have a look at that. So if we go to Analyze, I'll just get this down a little bit. If we go to Analyze Descriptive Statistics, Explore, and we'll put in standardized residual. Standardized residual. We'll put that in as a dependent. Okay, so that's all we do for that one. So we're not going to have any box plots at this point. Stem and leaf. We'll take that out. Okay, so that's the same one that we got up here. Okay, so in this case here we're testing to see that it's not way off. Now, having shown you that, what's an example of one that kind of falls off? Okay, so let's have a look at this. Now, this is me just bringing in some third-party kind of information. There's a patternless residual and constant variance. So they're the things that we're looking for in terms of assumptions. Today's remember is all about this analysis of assumptions. Ooh, look at the difference. Ooh, look at the difference for this particular example. So I'm contrasting now. Look at this fits plot, the residual plot. Wow, that's not a good fit. Look at this guy over on the right here that we just did with our data set. Okay, so what we've got there is our probability, and we've got our residuals. Also, what do you notice about this? The fits. This is a description of variance. Well, it has a pattern. No, that's not what we want. So we're using some visual cues to help us establish our assumptions. Okay, yeah, that's right, a polynomial. But that's not a linear, is it? So that's no good for what we're doing. All right, so it's important for you to just have a background, have a context. When we're looking at testing the regression model, what is it that we test the regression model against? Well, the first thing we start off with is some assumptions. And what are those assumptions? Is it actually linear? Well, that was an example of a polynomial. Is there independence, homoscedasticity? Is there constant variance? Are they distributed normally? And is the probability distribution normal? So all of these measures here that we're doing in the lab are really to check against that. Okay, so there's our plot. As you can see, side by side, standardized residual, and so we've been able to get those. So you've got some tools to go ahead and check your test for normality. Okay, what we've got, well, let's just keep going with this because we're going to do a little bit more analysis at the moment. Okay, there's our test for normality. So we've got the SW version, that's the Shapiro book version in the course, but the rest of it's pretty much the same in terms of how you analyse hypotheses. Okay, so the residuals are normally distributed. That's our hypothesis. Remembering last week that I did make a bit of a fuss about how to analyse hypothesis tests. All of our statistics are evolving to prove or disprove that statement. These residuals are normally distributed. That's an assumption about our linear regression model. Okay, so we need to show this and we need to prove it, and our statistics help us to disprove that. Okay, so are they what's the statistic and how are we going to choose that? Okay, so when you go back to your standardized residual table, looking up the top here, we've got our statistic and we've got our significance value. Okay, and those work together. Here's our statistic and here's our significance value. Now, I don't know, I have this thing where I use 50 thousandths. If I think about a decimal point, it just makes it a bit easier to compare things. So if I have a couple of values that I'm comparing against, how do you read your 3 decimal places? How do you read that? How do you say that? What does that one look like to you? Okay, now these often don't have the zeros on the back of them. How do you read that? Okay, how do you process each of those? So my tip for you is to think of this in terms of just the thousandths. Okay, and if they're not there, put them in. Okay, so if it's 0.06, put in your naught. That's 60 thousandths. Okay, same here, 50 thousandths. So this is commonly alpha, isn't it? 0.05 is 50 thousandths. Because you're being required, now what's this one here? What would we say for that one? It's 5 thousandths. Okay, so it's very easy to then compare 756 thousandths, 901 thousandths. So which one is bigger it's fairly easy to see. So 5 thousandths is less than 50 thousandths. So if P is low, HO's got to go. That was the phrase I used last week. So we'll keep coming back to that. So for our example, for the SW test, what we've got here is a HO which says that the residuals are normally distributed. Very good. Wonderful. Residuals are normally distributed. Is that the case? Okay. Is that actually the case? So are they normally distributed? Well, are they normally distributed? Well, we go and trust the statistics. The significance value. How do I say this significance value here? How do I say that? What would my version be? 906 thousandths. Now, is that bigger than 50 thousandths? Anybody? Yes, it is. It's quite a bit bigger. So that comparison method of using the p-value makes us decide, makes us have a decision. And the decision is whether or not we will reject or do not reject. So that's the next step. The next step is to make a decision and to stick to that language about the decision. So what I'm going to do is I'm just going to save this guy. Anywhere will be fine. And I'm just going to save it as a PDF. Go ahead. And I'm just going to pull that up. The SW, mate, we're going to, Justin, we're going to be using the SW. Okay, we'll always use that SW here. Okay, Shapiro. Okay, thank you. Alright, so I'll just get rid of that guy. And get us back to where we were. Because we looked at answering that part, that was good. And now we're here. Okay, great. Sorry, the reason I did that was because I wanted to do this. Okay. So the first step in making the observation about the significance of the SW test is to make a decision. Okay, and what is our decision based on this statistic and this level of significance? Our decision would be, so this is 1 mark. Okay, so I'm trying to be quite pointed. Our decision would be that's it. Well done. Do not reject. And finish it all off. So that's 1 mark. Okay, and the statement is the residuals are normally distributed. Yeah. So if we say normally distributed, then we're done. Okay. Alright, so sorry, I just moved that page unwittingly. So they're normally distributed. So we get our 2 marks for that part. Okay. So I think in that term, we're still getting used to the context, which is why I don't mind helping you guys with some of this. I'm not going to answer everything completely blatantly, but where I think it's still early days for you guys and you need that, we're talking about assumptions, we're talking about normality, we're talking about homoscedasticity, constant variance. We're talking about one thing that we just did there was that we made a statement about the normality of our plot. For this one here, okay, so we can see that this is this variance. So I've been able to give you a couple of examples of that. Alright, we checked the residuals for assumption of independence and constant variance. Okay, so you should be marking these off. Okay, you should be marking these off. as next. Okay, next. So we've checked that it's normally distributed. That's one of our assumptions. Now we're going to check for independence and constant variance. So how do we do that? Alright, so we're going to go to menu graph, and so our legacy dialogues, looking for our scatter plot, looking for our simple scatter, and define. This time we'll be looking at our standardized residuals again, which were just the observation, and so we'll do that, and that'll be our y, and our hours will be our x. So there's our graph. So that's not unlike what I showed you before with the other example. Okay, let's compare that again. So I'll just get that back. How do they compare? Is there a patterning? Is there a shape that's happening here? It's certainly not like this. Okay, so is there a patterning or a shape? No, it's pretty random. There's a little bit of distance between certain points, but at the end of the day that's okay. Alright, so if I go back to the other example, whoops, just to pull that over a little bit. That was the one that we said where it was okay. Alright, similar kind of plot, similar kind of scenario. Okay. No jokes. Let's stick to the program. Okay, you'll get me in a lot of trouble. Okay. Okay. So in this case here, we've gone through and we've defined our markers, and we've pretty much got the same plot. So if you've been able to do that with your SPSS, okay, sometimes I think it's important to be able to play around with things and get them worked through in a kind of reasonable way. Okay. So for independence, we want to see no recognizable patterns. So no lining, no curves, any of those kinds of things. And for constant variance, we want to see similar vertical variation. Okay, similar vertical variation as we move along. Okay, so we've got both of those, I think. Okay, so using this scatter plot, comment on the assumptions of independence and constant variance. So that's up to you now to put in there and say, okay, from the pattern, using visual cues, we're looking for no recognizable patterns. There's no lines, there's no polynomials, somebody said. There's no curviness. It's all independent. So we can say that independence is verified from the nature of the visual lack of patterning. Okay, the vertical variation is good as well, and so we can make a comment about constant variance. Okay. Now we can check the independence assumption with a DW statistic, which is available from the SPSS output produced when we built the model. So basically, I guess what this is saying is we can do the same thing, not just visually, but we can do it from a statistical point of view. Okay, which is what we like to do. So we're checking this value here, and I just want to get the other one. There we go. Sorry, I'm just having a look for our model summary. There it is there. Okay. So it was no fluke. Okay, so we've basically got the same information that's in the lab. Sometimes you just got to go for a look. Okay. Is there any statistical evidence that the residuals are not independent? Is there any statistical evidence that the residuals are not independent? Okay. So we can use the model summary to help us determine that. You know, we've seen R square, we've seen our standard error and our DW statistic. Okay. So 2.393 gives us an indicator that there's not sufficient evidence that the residuals are not independent. Alright, so the next thing that we do is we have a look at, so you should just mark these off. Now we can check for influential points. What's an influential point? What would be the definition of an influential point? I'm not so sure. What do you think? What would be an influential point? Yeah, but what is it about the outlier? What would be the idea behind the outlier? Yes, an outlier affecting the model. An outlier. Actually, let's take the reverse of that. I'm just going to do a little sketch, I think. So let's take the reverse of that and think about an outlier where, let's go back to this drawing. We can take that one away. Let's go back to the drawing and let's think about an outlier where it didn't have an impact. Let's do the reverse case. So if we did do a regression and we had our data points, we had a whole bunch of data points, and we saw that way up here somewhere, that data point, okay, if we remove that data point from the model data and remodel the data, would it impact on the model? Or to what degree would it impact on the model? Okay, so this is what this Cook's distance is all about. It's about making a decision about one data point and then suggesting what the implications are for the model with or with that missing. Okay. Alright, so how do we go about doing that? Alright, so if we go back to our graph, our data, and graphs, legacy plots, a box plot for our data. We'll do simple. Just change that to separate. Okay. Then we'll get Cook's distance, and we'll use Cook's distance in our boxes. Okay, so now this is representing the distance, and okay, so this is our representative view of the distance processing with its incumbent percentages, and look at what we've got. They've got a data point 13. Okay. Now, using the relevant statistic, can we work out if it's an influencer? Is it an influential point? Okay. So if we go back to our lecture and we look down for influential points, they're all about normalities and fits. Okay. A greater influence on a model parameter. Okay, so this is where we're talking about the existence of this guy and whether or not it's influencing the model. Okay, so we'll use our statistic to help us understand that. Okay, so here's our distance. our D, independent variables, studentized residual used in residual analysis, so that's what we're doing here, okay, and we're looking at this from that point of view. Okay, so we'll go back to this one. Great. Okay, so using the relevant statistic, identify any potential influential points. So clearly the potential influential point is 13, data point 13. Okay, so what we can do is have a look at rebuilding the model. And so when we identify, so we'll just do this now for answering this part. So when we identify potential influential points, we exclude them and rebuild the model. Okay, so we exclude them and rebuild the model. So what I want to do before I just go and rebuild that model is I just want to go and get the coefficients. I just want to go and get the coefficients. Now what I'm going to do is take a screenshot of that, so just bear with me while I do that. I'm just going to take a screenshot of the coefficients. If it's going to let me do that. Sorry, sometimes when you use the technology, it does that. So I'm just going to grab that. Okay, I'm just going to come over here and grab this screenshot, and I'm just going to save that for the moment. I'm just going to leave that over there. Okay, so sorry about that. All right, so rebuild the model. Okay, so that's the thing. When we identify potential influential points, we exclude those and rebuild the model. So that's why I just stored this data, because I want to call it back up in a minute and compare them. Okay, if we estimated beta coefficients in the reduced dataset model have changed significantly from the full dataset model, which I just took a snapshot of, okay, we retain the reduced dataset model. Otherwise, we return to the full dataset model. Okay, so there's some decisions there. There's a lot in that paragraph. Okay, additionally, if excluding the points improves the behaviour of the residuals with regard to the assumptions, so there it is. That's the nub, isn't it? That's a real statistical intelligence. If the excluding the points improves the behaviour of the residuals with regards to the assumptions, so you can make note of that. We retain the reduced dataset model. Otherwise, we return to the full dataset model. So it's all about doing that. Okay, so this is the part that we're on now. We're going to see if this influencer affects our data set. I've kept a copy of that beta coefficients, and so we're going to see if this change in data impacts on our beta coefficients, which I've stored now. Okay, so we go to transform, and we go to compute variable. Hopefully, is it all making sense in terms of the strategic intent of what I'm doing today? If people could just feed that back to me, is the strategic intent of what we're doing here today? It's all kind of nutshelled in that paragraph there, but are people happy with that? If you could just feed that back to me, that'd be great. Are you happy with our strategic intent? Okay, because our assumptions are very important, and we're testing that assumption now. Okay, thanks for that, Matt. I appreciate it. All right, so we go through compute variable, click in target value, and in target value we're just going to put a name. This is going to be the header of a new column. So this we'll just call it filter _1. I think I can do that. Okay. and in the numeric expression we're going to put our filtering agent is going to be 1. So any this new column that gets introduced, if it's got a 1 in there, we're going to include it in the data set. So that gives you a clue as to how I'm going to exclude things. Okay, so what's happened there, in the data set we've created a new filter 1, filter by 1, and so we've got all of our 1s here. Very good. Okay, so we've added to our data. In that sense, we've added a filter variable. Okay, so that's been included. All right. Now we want the software system to redo this computation and building of the model, and we want it to include the filter. Okay, so we've got to go and tell it to do that. So that's the step we're at now. We're telling it to include this filter data as it rebuilds this model. Okay, so the data menu, we're going to select cases, and select cases isn't far away down the bottom. Okay, we're going to come down here and tell it to use a filter variable. Okay, and I'm going to click on my filter variable and populate that field. So as it produces data, I want it to include this filter variable. Okay, so we're including the filter variable in that. Okay, so if we go back to our data editor window and see the impact of what we've done there. Okay, so if we go along to this observation 13, this is this guy here. Okay, now if I go into my filter column and make that a 0, you'll notice straight away that it crossed out. All right, and now that's saying that we are going to include or not include data point 13 because it's got the filter variable 0, not 1. Okay, so if we rebuild the model now and look at our betas, because that's where we're headed, right? We're going to look at our betas and see if in fact there's any change based on this all-important paragraph. Okay, this is a very important strategic intent as far as your residuals and errors go. Alright, so it's now got a slash through it, so any computations we're going to do will not include that. Okay. Alright, so we've got to go back and repeat that. Now rerun the regression on the filtered or reduced data set. Okay, so we go to Analyze, and what we're looking for is linear. Where are you? Sorry, I'm going to go back to the instructions at the beginning because you might be in the same position. And we'll go back up here. Yes, I know. Keep going. I know, there it is. So just making sure, I know you're better than me. You're all smarter than me. I know that, you know that. So just humour me while I go back and find it. Okay, so we're looking for regression and then linear. Okay, so thank you for being patient with me. Okay, just think, yeah, it's just a binary column. It's just going to tell us whether or not that data is included. So we're going to rerun the model now. And because we've put that filter in and we've told the system that that filter is in play, this will go ahead and redo this. Okay, so none of that changes, and when we press OK, we get now a new set of summary. Okay, a new set of summary data, and look, we've got coefficients. So this is our residual statistics, our charts, all of those things are still there. Okay. But now we can compare them. So this was our regression step. I mean, I can run up the top and look at that and compare them that way. That's a bit trickier to do. Okay, it's all there. I mean, all the data's there, but I took the time out before to take the coefficients and compare them. So I'm just going to bring that back and probably just reduce the size a little bit so that you can see quite clearly what's going on. So we now have a difference in our reduced model, which is here, and our original model, which included point 13. So if we go to the beta columns, we can see BO and B1, B0 and B1, okay, and from that we can make a comparison. We can see the change in the bounds, we can see the change in significance, okay, if any, we can see the test statistic, okay. So we can use this comparative idea to help us make some decisions about the nature of that data point. Was it an influencer? To what extent was it an influencer? Okay, so there's a little bit of computation that needs to be done in order to answer these last parts of the tutorial. So I'm going to write those down on the paper, which I'll do in a moment. Alright, so you're happy with where we're at the moment? Okay, we've got the whole purpose of the paragraph was to compare two sets and then make some statements about the two sets. Okay? Alright. So going back to that one and getting back to where we were. Thanks for being patient with the old man. And so we've got some things here that we've now rerun the regression based on the filtered data set. Calculate the proportional changes in beta coefficients between the filtered and full data set models. Okay, so let's have a look at the computation. I'm just going to pull this window over here and squeeze it down because I just want to see coefficients. I'm going to get that one there and squish that down as well so that I can just see the coefficients, and still hopefully we can see, yep, and we can see the question in the middle here, calculate the full proportional changes, and I want to click on that. So we've got all the data there that we need. Okay, so we're comparing proportional change. Okay, so as a principle, the proportional change will be, as I'm doing this by hand, the proportional change is basically the new or the reduced, that's our new one, subtract the old, divided by the old, and we usually express it as a percentage, and that will be our proportional change. Okay, so that will give us an indicator of what the impact of this particular data point 13 is. Okay, that says old. I'm getting old too. There you go. All right. So what have we got? So we've got to take our two coefficients. So the old one's up the top, the new one's down the bottom. So make sure you use all your decimal points. If it's given with 3 decimal places, don't get skimpy and do that. So we're doing BO. So we've got beta O hat. So we've got 13.9. What is it? 13.941, and the original one that we had was 22.164, and as a proportion of the original 164, including all the decimal places, times 100 over 1. Does somebody just want to put that in for me? Well, we're doing that now. We're working out the extent of the influence now. I'm going to give you a percentage. Okay, the Cook-D, yes, the Cook-D test is what we just did. When we did the Cook-D test, put the residuals through that box. You can go back through and check it, but we did the clicking of the Cook-D in one of the elements there. Where did I put it? Yeah, 37%. That's the right one. When we did that Cook-D, there it is, we put the Cook distance in. Okay, so that was hopefully answering your question. Okay, so coming back to this particular problem, we've got to do some manual calculation and calculate the proportional changes between the filtered and unfiltered. Yes, it does matter. Yes, it does matter. Okay, because that says that there's a pretty big reduction of minus 37%. Now, notice I didn't say an increase. I said a reduction. So the minus tells us that. Okay, so it tells us use that language carefully. Reduction or increase. It's a reduced set, so I'm not playing on words. I'm not being a smarty. reduce or increase. Increase. Okay, and the negative will help you do that. Okay, so it's important. It's important to take notice of that. Okay, all right. So and what about for beta 1? What about for our estimator for beta 1? Let's see what that is, because that's only where it crosses the y-axis. This is the gradient. This is the one that's probably more interesting. So we've got our new one for our variable. Subtract our old one, divided by that 9.992. Can somebody give me this one, please, if you wouldn't mind? Okay, so however many points we use. So what is it to 3dp? Is there something we can do for 3dp? 23.29%. So that's any increase or a decrease? Okay, so what we've done there, that's right, and that's what you need to say to get your two sets of marks. It's not good enough just to put the percentages. You've got to say a reduction, okay, and an increase. You've got to make that point, because that influencer, this is the whole point of analysis, right? We're doing the analysis part of regression. We're comparing our residuals, we're looking at the impact of data, and we're seeing whether or not those things have changed. We're going to have another look at that, okay? So to get that part down pat, it's important for you to make sure you're able to do those things, okay? All right, so stick to your decimal points. Okay, so all right, so the next thing is sorry, while I just get my house in order. All right, so we've done that little part. I'm happy with that now, so that's good. All right, the proportional changes in the beta coefficients are large enough to worry about. So the filtered data set or the reduced data set should be preferred. I mean, a 20% change in the gradient, or the gradient represents what for B1? The nature of the regression relationship, doesn't it? So that's a big change, a 20% change. That's not 2%. That's a big change in the nature of the relationship, and where the y-axis gets, where it falls, is a change also. So there is a significant change. So what can we say about that? It's an influencer. It's changing the nature of our model. So the proportional changes are large enough to worry about. So there's our and the preferred model. So you need to make that statement as well in order to get those marks. All right. All right. So the next thing we want to do is a little bit tricky. So we've been given some t-distributions. Now I'm not sure to what degree you've been trained in looking up t-values, but it now comes back to the idea of one-sided, two-sided alternative tests and which one we invoke. Okay, and that goes very much to what we're looking at now. Okay, so for part G, it says use the significance level to perform a hypothesis test. So I've just sorry, I'm just going to put that so that I can see it like that. Use the significance level to perform a hypothesis test, okay, to determine if the true value of the slope coefficient, so which one's that, beta 0 or beta 1? Yep, beta 1 in the filtered data set is less than 1.537, okay, less than 1.537, and well, where's our 1.537? So write down the hypothesis, the test statistic, the result of the test, and a conclusion in non-mathematical language. Okay, so this means we're going to have to do a hand computation and do an estimate based on the model statistic. This is what we're comparing. Okay, now the first thing I want to do is point out in this question, it's a 4 to 6 marks question. So I'm kind of betting that if Joanna puts this in a test, it'll be a 4 to 6 mark question, and this would be considered like your core competency in terms of hypothesis testing. So let's just spend a bit of time on this so that we can draw it out. The first thing I want to draw your attention to, we've identified the slope coefficient, and we want to see if the slope coefficient statistic tells us is less than 1.537. Now the reason that I've bothered with that is because the less than implies it's going to determine for us whether it's one-sided or two-sided in terms of the way we form the hypothesis. Okay, so the hypothesis formulation now is quite important. Okay, so I just want to go back to this one. Sorry, while I look up, making sure I make sense of everything. Okay. Alright, so sorry, I'm just lining up my ducks and making sure I get it exactly right before I speak. I don't want to send the wrong information out, so I'm just making sure I get it exactly right. Okay. Okay. So our beta 1 we've got to form this hypothesized value, and we're going to have to use a t statistic. Okay, so we're going to have to do it by hand. Okay, so what's the t statistic going to be? Okay, so it's going to be the estimate, subtract hypothesized, divided by the standard error. Now if you go looking for it, you'll see it in your notes. Okay, so we have to do that t statistic. Okay, the next thing we want to do then is we want to define our HO. HO is going to be beta 1 is equal to what? What's our hypothesis? Anybody? Yeah, that's the thing, isn't it? That's what's in the, this is the thing. Yeah. Okay, so we're just going to pause so Justin can think about that. Because these hypothesis tests were zero. They were zero. Okay? They were hypothesis tests based on being zero, because that's what you were taught. Okay, that's right. So in this case, oh, now Ayusha, I'm worried that you've got that not matching what's in the question. Okay, so I just want you to think about that while I go on with this. So the hypothesis for these guys is always is beta 0, that's no relationship. And disprove that, H1 applies. Okay, so the alternative hypothesis applies. In this case here though, this is specifically saying to test whether or not the slope coefficient isn't 0, but it's 1.537. Okay, so our null hypothesis is testing whether or not it's 1.537. So that's a big deal, guys. This is a big deal, okay? I'm making the emphasis, I'm spending the time because I want you to be able to say, what's the difference between, why was it 0? Why is beta 1 0? Because that's about relationship, isn't it? That's fundamentally about whether there exists a relationship. And our statistic disproves that. This particular question in the reduced data set is asking, is the comparison to a number, not 0? Is it 1.537? Okay, so this is where the course gets a little bit, you're now at the high end, okay? This is the high end of the maths stats part of this statistics course. As long as you understand why beta 1 is equal to 0 under normal circumstances. Somebody want to just tell me that? Somebody just, why is beta 1 normally set compared as a null hypothesis to 0? What does that tell you normally? So forgetting about this reduced set and what I've done here, when we normally set beta 1 to 0, why do we, if there's any relationship, thank you Matthew, is there a relationship? And if it's 0, well, if it is 0, if we affirm and do not reject the null hypothesis under that circumstance, that B1 is 0, what does that tell us? There's no relationship. So if we did not reject it, there's no, thank you Matthew, yeah, no relationship. Okay, so now we're thinking. Alright, we've progressed this concept now a little bit further, haven't we? Because that's not the only paradigm. Sometimes now we're not checking if there's no relationship, we're checking if it's the relationship of 1.537. Ah, can you do that? You sure can. You can test it for any number. Okay, so in this case we're testing it for a relationship of 1.537. Okay, so we need to have an alternative. Where do we get the hint for the alternative from? In the question. What's the question say? The question says less than 1.357. Yes, thank you. Okay, so our alternative hypothesis will be that beta 1 is less than 1.537. Now that has an implication for the comparison and distribution. Okay, is it two-sided or one-sided? One-sided. It's down here, isn't it? Okay, and so that's our hint for using the table. So the little table that's there, okay, we've got a significance of 0.05. We're not going to halve it. It's not alpha on 2. It's just alpha because it's one-sided. Okay, so the critical value that we're going to be comparing against is the minus 1.73 value. There it is there. Okay, minus 1.73 value. Okay, so we'll get our minus 1.73 value. That's our comparison value. That's the critical value with degrees of freedom from your student's table. Okay? Okay, HO is only ever equal to. This is a fundamental idea now. We never ever use any other maths in the HO part. We never ever use anything other than equal. And the reason for that is because hypothesis testing is a proof by exception. So we can't have two things to compare. It wouldn't work mathematically. So we just have the one. Now we either affirm that equate, or we disprove it. That's the exception. So that's the mechanism, the mathematical proof mechanism that's giving you something to deal with in terms of beta. Okay, does that help? All right. So it's a mistake to ever put anything other for HO other than equal. It's a complete mistake and you'll get 0. And it'll impact on the rest of the question too. So you can take an ironclad guarantee from me. Jason said null hypothesis must be equal to. Okay, whatever it is, whether it's words or whether it's whatever, it must be equal to. Don't ever make it anything else. Okay. All right, so we're getting closer. We've got to do our T statistic now. Our T statistic. So which one are we going to be using for our new reduced data set? So beta 1 for the new reduced data set is so if you look down here, this is our reduced data set. So looking at the coefficients, that's all right. Looking at the coefficients, we're looking at 1.223, don't we? So the estimate is 1.223. Remember, it's an estimate. Okay. What was the comparator? 1.537. And what's the standard error? Where are we going to get the standard error from? I'm giving you a bit of a hint there. There it is there. From the outputs. 0.177. Well done. If you do a computation, you'll be able to tell me what that looks like. Please, if you could tell me what that is. What's this computation here? Yep, minus 1.774. Okay. Now notice the decimal places, how important it is. Because we have to, at the significance that's at the 5% significance, what that means is that this area here is a value of 50 thousandths. That's the area. Okay, that area is 50 thousandths. Okay, that's the level of significance. Now, in terms of interpretation, our 1.174, where does it fit? Our minus 1.774, where does it fit? Well, there's 1.73, so 700. So this is where my thousandth thing plays a part. I think anyway. Okay, 730 thousandths or 774 thousandths. Which one's bigger? Which one's further to the right? And which one's further to the left? Which one's further to the out? Ooh, well, I'm not sure what you mean by that, Justin. Out? Is it in this region or over here? Further to the left. Great. Okay, so this 774 thousandths is more than 730 thousandths, so it's more negative. So this particular one is appearing here, approximately. Now, I haven't drawn it to scale because it's conceptual. Okay, so that test statistic is occurring in the rejection region. Now, one of the things that carries over from primary school is the problem of the negative number line. So just use the thousandths idea. 774 thousandths is greater than 730 thousandths, so it's further to the left. Okay? Yeah. Okay, further to the left. Okay, 774 thousandths is a bigger number. Alright, so that's good. We're working together, guys. You know, this is a safe place to learn. That's why we do this. I have a passion for teaching, and I love to be able to support you and help you out, and that's what this is all about. So there's nothing, there's no errors here in my work with you. Okay, it's just about getting these concepts right, because this is a fairly big deal, right? Alright, so what we've been able to do is we've generated a test statistic, we've made a null hypothesis, we've made an alternative hypothesis based on the language of the question. That's very important, okay? And then on top of that, we've been able to make a decision. So what's our decision? Reject or do not reject. Yep. So our decision is to reject the null hypothesis, and that tells us that the new beta is not equal to 1.537. Okay, so under 0.05 significance in the area of this point here, we can say then our statement, okay, our statement's going to be that beta 1 it's statistically significant. Okay. Alright, you happy with that? So we've got full 4 to 6 marks for that particular one. Okay. Alright, any questions or thoughts? Are you happy with that conclusion? It's very, very important that you make this last part stick. Okay. Okay. All right. So the next thing we want to do is we want to consider the last part. So we're heading towards the last part now. Okay. Now the coefficient of determination for the data set. How is this related to the variables in the model? So we're talking about R squared. Now, what is it about R squared? What do we know about R squared? What's it tell us? What's R squared tell us? That's a really good way to put it. I really like that. How much of the variance is explained? I really like that way of putting it. How much of the variance is explained? How much of the variance in X explains Y? Is that a reasonable way to put it? How much variance in X explains Y? And what that says is that 73% of the variance explains Y. 73% of the variance in X explains Y. Okay? So in that sense, that gives us a good indication of the relationship between the variables. Most of the it's nudging that 75%. Some people say 75% is the threshold, but you can ask Joanna about if she's using 75%. But some people say that 75% is the threshold for determining the relationship. Okay, how much of the X is explained? I think that's a less threatening way to put it. So the coefficient determination of the filtered data set. So I'm just going to pop this back up and grow it again and just pop this one away and just bring this up for us to see. And where's our R2? There it is in the model summary. Okay, so in the model summary we've got an R square of 0.737. Okay, so in that sense what that's telling us is that there is a relationship between these two variables. Okay, so that will be your statement. Your statement will be the coefficient of determination R squared it is explaining, I like that style, is explaining 73% of the variance. Okay, I think that's how you would phrase that. Explaining 73% of the variance. I think that's a good way to put it. Okay, so how did we go? We got to the end? I think we're there. We've got to the end. Okay, so hopefully, no, that's from the new part, mate. That's the new statistic I'm showing you there. See where I put regression? That's when I went up as an old man and got the regression. Okay, so that's the new part. The old part, I don't think I got the summary statistic in the capture, but you can do that. You can do that yourself. Okay. All right. So hopefully that's given you the insight that you need to participate appropriately in tutorial 2, lab 2. And hopefully I've been able to nut out the detail for you in terms of what's happening with particularly the hypothesis testing. Okay, yeah. Okay, so are there any further questions? Is there anything else that I need to cover? Has that been a reasonable use of our time together to go through those concepts and work that through? Okay, all right. So I'll hang around for a little while if you have a particular case, but basically I'm going to dismiss the group now. So we've managed to get through the tutorial, and I will put a link up for repeating this video. I'll put it up on YouTube and you can watch it there. I'll check that with Joanna though. Okay? Alright. Thanks very much everyone. Okay, thank you. Thank you. Thanks. Thank you. Thanks, Albert. Thank you. Yes. Yes, so Cook's distance, part E. Where we go? Part E. Where is it? Yeah. Calculate the relevant statistic. Yeah, so that's Cook's statistic. Yes, Cook's distance, yeah. So in identifying any influential points, we could say that because of the reduction in the beta 1 and beta 0, and we just proved it statistically, that we could say that it's a statistically influential point. I think one of the things that comes up is what happens if you have a lot of them, and unfortunately if you have a few of them you've got to do them one at a time, and you've got to redo all of this every time just to see what's happening with the individual one, and then you plop that off. And I think in the actual, I think in the lecture there's a bit of a demarcation, isn't there? One of the slides has got, I saw something, oh yeah, this one. Okay, so Cook's distance here was showing a whole bunch of them, and a good question to ask is what do we do when there's more? Well, first of all, I don't think Joanna will give you an exam that requires multiple analysis. I think it'll just be the one. Okay, so I don't think you need to be fearful of having heaps and heaps, yeah. Okay. So you've all been able to get your IPSS working? Yeah. That's good. Okay, it's just a matter of working your way through it, isn't it? But hopefully that's clear now with the various computations and what's required. And how's your hypothesis testing going? You guys happy with the way that's unfolding for you? Yeah, you're right. I normally say when I do the introductory course, because I teach one of the other subjects, and I normally say to students with hypothesis testing it might take you a month. So that's a full month, 4 week, 4 full lectures before you start walking out thinking, I know what's going on now. It does take a while. It does take time for hypothesis testing to sink in. But if you can remember a couple of basic rules, it does help. Alright guys, I might call it quits there. Okay, unless you've got any other particular things. Justin, yeah, I need to talk about it, exactly where the video goes and when. So I'll do that in the next couple of days. Just remember it's a public holiday tomorrow and Monday, I think. Yeah. Alright, see you guys. Thank you. So James and Ashtush, you guys are going okay? Okay,